Yeah, sorry for the delay. It's a bit of a mess with the laptops. So this is a PDF version, so some GIFs don't work. Yeah, I guess we have to live with it. Anyway, so where did I start? I mentioned my name, I mentioned the organization, the title. I go to the real problem now. There is a database where all the renewable energy of Germany is collected. It's in the Bundesnetzagentur. It's called Marktstammdatenregister. I call it here Energy Data Register. So there are all the photovoltaic, wind energy, biogas, you name it. It's all there. And who is putting the data inside? It's actually the owner of this renewable power plant. So if I buy a windmill, I'm obliged to put this data or my information into this database. The location, how high is the windmill, what is the length of the wings, what kind of turbine, where is it placed, and when will it generate electricity. And a lot of media organizations use this open data to publish nice articles like this. So where will all the new windmills be located, or how Bavaria is blocking the expansion of wind power and so on. But in reality, the data is quite inaccurate, let's say. And on the right side, you see just a plot of this data set with onshore windmills in Germany. And it gives you already a good indication how wrong it is. I'm not blaming anyone. It's sometimes if you fill in data manually, you have a typo with a location, and we are all humans, we do errors. But the accuracy of the data set could be improved, let's say. And why do we need precise power plant locations? Well, for strategic energy planning, for the effective repowering, also to plan where can we remove old windmills to replace them with new ones, right? So this is a normal thing to do nowadays. And you think of Germany, we know we are working precisely, but sometimes, as you see, we don't. So to show you an example, I hope you see the orange dots. This is actually the real data, but you also see many of them are in the wrong location, as I just stated before. Some of them you could think, well, it's a general error that if you move the points on the right side 200 meters to the north, it would fit somehow. But then on the upper left, you have a point somewhere between two windmills. So which one is it now? And then you have the ones in the brackets, you have windmills, there's no point nearby. So this is a bit of a mess. So this is the problem we have. And the people in our agency, they're aware of this. And what they want is they want the actual locations of the windmill. And this is where we as the AI lab now come into the game. And we say, well, let's try to detect them based on remote sensing. It's a beautiful remote sensing case, object detection. Let's try if we can improve this data set. For these tasks, we need satellite data and we need training data. So this is the part where I explain a little bit the satellite data we are using. As a federal agency, we have access to Planet data. Our agency has a contract with Planet, so we can access Planet base maps. Planet produces these base maps on a monthly basis. So what they do, basically, they have these little doves. They take daily images, and what Planet is doing, they're stacking them based on cloud coverage, and the best scene is on top, and they create a mosaic for whole Germany based on these data sets. The product comes with surface reflectance, 8 bands, so it resembles somehow Sentinel-2. The spatial resolution is 4.7 meters. And what we have access to at the moment is a scene from April, June, August, October for 21, 22. But we can order new ones as we go along. And we download these with the Planet API. These are the satellite data we are using now. I'm talking about the training data we use to label basically the windmills. So As you can imagine, no one has the time and the guts to do this manually. So we are actually using manually labeled data from the UFZ. This is the Helmholtz Center for Environment. They were actually manually labeling them and published a data paper about it. They not only labeled windmills, they also labeled photovoltaic, biogas, and so on. So we use the onshore labels for the windmills, and we're only interested in the location, basically, and not so much in the attributes they provided. How did we do that, actually? So here's a small scene of October 2022 from the planet base map. If I overlay the manually labeled data in the blue dots, we followed basically 4 different ideas how to create a label. The first idea was what the model needs is a bounding box, and we create these bounding boxes automatically based on the lower right is the actual windmill, and we try to cast the whole bounding box along with the shadow this windmill is creating. And this was the first idea we had. The second idea was to create just a bounding box based on 50 meters around the labels. The third idea was to use, according to each windmill, the wing lengths. So bigger windmills have longer wing lengths, smaller ones shorter, so the bounding boxes, they vary. And the fourth idea was to use a bigger bounding box to include partially the shadow, but also the surrounding of the area. And now I'll go a little bit ahead of myself, but the solution of the wing lengths was basically the best solution. And I continue showing results for the solution number 2, basically this one, the green arrows, or the green bounding boxes. This is how the label distribution looks like. When you do this object detection, you should try to avoid that your labels are always in the middle of the image chips. The image chips are 640 times 640 pixels, and we tried, you see that on the left, to have the labels spread all over these image chips, that they're not only clunked in the middle, that the model is learning, okay, the windmills are always in the middle of the image. And the distribution, or the label size distribution, you see it on the right. So this is what I mentioned before, that the bounding box is basically, the size is according to the wing lengths of the windmills. Now we have the satellite data, we have the labels, and now I'm talking a little bit about the model. When it comes to object detection, there are many different options, but we chose from Ultralytics YOLO, you only look once, which has a very high processing speed and an impressive accuracy. We're not so much interested in speed. Speed is not an issue for us, but the accuracy. But moreover, this model is open source, so there are no licenses, well, commercial licenses attached, and we are basically free to go. So this model is not only one model, it comes in different flavors. Ultralytics provides large, medium, and small, and extra large models. And well, extra large models, they need longer to crunch the data, and smaller models, they need, they do the whole thing in a little bit faster, but obviously bigger models, they are probably more accurate. And we tested basically many of them. So we tested version 8 and version 9 in different sizes. This is how basically our training data look like summarized. So we used YOLO version 8 and 9. At the end we have, I mentioned it before, we have 2 years and 4 months. So combined we have 8 different data sets. And we used for every year 8,000 images times 8. So we have about 47 or 74,000 images, 340,000 labels. But what we also created was empty image chips without labels. And in these empty image chips, we tried to show the model how tall objects look like, which also cast a shadow, like you could think of a chimney or a construction crane or high voltage power towers. They're all large, cast a shadow, and the model could confuse these objects with windmills. So we collected, based on OpenStreetMap, many different thousand locations where we could show the model, look, this also exists in Germany, but this is not what we are after, okay? Yes, and this is here one example of the training data where we have a batch size of 16 images here. And the training for the best model took 10.5 hours, and we are using, well, as a federal agency, we cannot really use Microsoft or Google or the other big players. We are a bit more restricted, and there's a platform called Code.de. Some people may know it. It's a bit like Google Earth Engine, but less powerful and has less data sets, but you get your GPUs, and it's for us free to use, and it's pretty safe. So we are using this platform, and we have some GPU machines for that. So how do the results look like? So here basically we show the different runs we have. On the second left column, you see the different models, the different model names and the sizes. And you see the batch sizes we used. So this was a bit in trial and error. We always used 60 epochs. And this is probably then for us right now, the most important criteria, the precision. And in that case, we had a precision of 92, 93%. And of course, we were trying a little bit different settings, but we figured out that this kind of setting here with YOLO version 8, the normal size model gives us the best results. Of course, when you train a model, you have this test set and validation set. So we had true positives of 97,000 in the test set. And that boils down to a 93% true positive, but we also have a high amount of false negative. And we tried to dig deeper. Where are the false negatives, and where are our problems basically? And we found some explanations. I hope you can see it. On the left side is basically one of these image chips with training labels for our windmills, and here's one marked in red. And you see, or I hope you can see, that the windmill is there, but it's not really central, so it's a bit shifted. This is probably due to, let's say, a small digitalization error when you create the data set, the training data set. The model, on the other hand, on the right side, predicted or recognized the windmill correctly, but now we have a small mismatch between the training data bounding box and not perfectly overlaying with our result bounding box. And we say it has to overlay at least by 40% to count it as a hit. And if the overlay is less than 40%, then we say it's not recognized. And in this case, the overlap is less than 40%. So the model is good. The model recognizes the windmill, but according to our wrong training label, wrong in the sense of a little bit shifted, this is actually, in this case here, a miss or false negative. Another case is false positives on the left side. We have again the labels, but here are two windmills which were not labeled. So I mentioned before that the training data were manually labeled by the UFZ, and here again 2 were missed. The model recognized them, but because they were not in the training set, so this is also an error. It's not a real error. The model, as we see, performs well, but in the confusion matrix, this appears as an error for us. And now I try to, this is a combination now to try to explain the causes of these false positives. Is if you look on the lower left, there is the dot, which is slightly shifted a couple of meters to the real location of the windmill. So this kind of training data errors, we take them also into our model, and we basically train the model with wrong training data sets. And as you also see, I hope you see, is that the satellite images also have a small shift. Here, for example, on the lower left, the bounding box or the windmill is slightly outside the bounding box. And here in June, the windmill is just touching the bounding box. It's not that the bounding box changed, but the image below changed. So Planet, I probably guess they do their best, the best they can to georeference the images, but there is a slight offset in the images. So both kind of errors come together here. This is how our results look like in the inference. So the orange data sets, or the orange points is the training data, and the red points are our correct classifications. Looks pretty good to us. We have some misses here and there where we need to find out what's the reason. And on the right side, you see again basically the problem I tried to explain in the slides before, that you have that the model detects the windmills quite good. Yeah, so the red dots, and here, for example, the orange dots, this is the dot for the training data, and it's basically wrong. So what do? Our solution is now that we take our own results, the red dots, and create a new model. So we are retraining a new model based on the first model. And we got yesterday the results, and they look, for our standards, pretty amazing. So our accuracy goes up again. So we are now at 97% accuracy. So we could cancel out a lot of misses. I mentioned before that we gave the model a lot of empty image chips with, and these image chips had high voltage power stations or power towers. And here we see that some of them are still recognized as windmills. No, this one here, this is a Google satellite or aerial image, and here you see a misclassified high voltage power tower, and this is how it looks in the Planet base map. And yeah, we still need to add more images to show the model, okay, this is not what we're after. I mentioned in the beginning that the German landscape of windmills is changing. So the oldest generation of windmills is slowly removed. So the oldest ones, they are 20, 25 years now old, and they don't generate as much energy as the latest generation. So they are dismantled, and new windmills are constructed. And we also try to detect this or create a certain pipeline to detect this. So I show you here the 8 Planet base maps, and we have the detection dates mentioned on top. So it detected basically the existing windmill correctly in the year 21, and it was dismantled in March 22. And then in March 22, our model also recognized, okay, here is actually no windmill anymore. And it does a good job in this case to detect the dismantled windmill. But you can also see that already here, the old one is replaced with a new one. And of course, the new windmills, they are in a different location because the wing lengths requires different distance to the next windmill, so they are not exactly in the same spot. But here's a nice example of a repowering old against new. Small outlook. I mentioned it before, I think we need more unlabeled data. For example, high voltage lines, chimneys, construction cranes, and so on. We were also thinking on adding to Planet data Sentinel-1. because it should stand out in the data set, to think more about the logic pipeline of this dismantling detection, and also think about how we bring back our results basically to this energy data register. This is basically part one of the presentation, and now part two, I try to talk a little bit about what we can do with the location. Now we identified the windmills, and what do we do with it? Some of you may know that satellite images are not basically images. They are sensed by the satellite one layer at a time, and there's a certain temporal offset between each layer. So layer red, green, and blue, let's say they are 20 milliseconds apart from each other. And if you see, for example, a moving object like here, the airplane is moving, the satellite is moving, takes every band in a different time, and suddenly you have the airplane 3 times. Yeah, so it has a temporal effect. And we try to use this temporal effect to recognize the activity of windmills. Once again, here now you see that basically in Sentinel with the 8 bands, each band is taking in a different time, and you see an object which is moving always in a different spot. And not only Sentinel has this temporal effect, also Landsat and Planet itself. Yeah. So when you have moving objects, you can basically detect them, and it gets such a rainbow effect, or a plainbow effect in this case. The question now is, could you, well, you have to imagine in a PowerPoint that the right side is a GIF and the shadow is moving. Yeah. Just close your eyes and think like, okay, this shadow is moving. It looks really beautiful, and it is not a moving object. The windmill doesn't move, but the shadow is moving, right? And you see this on the lower left, and you see the little bit here, when the light would allow, you see here a little bit also the wings always in a different position, and it creates such a rainbow effect also around the wings. And you see the wing location in this blue, green, red, near infrared scene always in a different spot, which indicates to us, okay, this windmill is actually moving and generating power. And keep in mind, this is one image. So it's not 2 different images, and this is one moment in time. So the question was, is it basically possible to detect the activity or the movement of wind turbines in one image? And we had Felix. He was a bachelor student to work on this problem. And what he did is he basically downloaded, this was before our wind detection project, so he downloaded the data from OpenStreetMap, 4,800 wind turbine locations, and he downloaded for each location also the Sentinel-2 from Earth Engine. And then he cropped the images around 40 times 40 pixels. And then he did some cloud masking and some histogram matching so that the 4 bands are matching nicely together. And then, of course, the GIF creation, so you get this little video of a moving shadow, and then he started labeling active or not active. And the shadow I showed before was quite nice, so it's not always as nice in reality. It's not as clear. And so he could find almost 3,000 active windmills and a couple of, let's say, 110 not active, and some were not recognizable. It was just impossible to say, is it actually moving or not? Why is that? Let's say on the upper left is good quality. It's not really good quality, but let's say for this example, it's a good quality image. Sometimes you have in Sentinel-2 still some remnant clouds, and you don't see the shadow, or the shadow falls on vegetation, on a forest, and the forest kind of eats the clouds away. So it's really not, by a human, not really, you cannot really tell if it's a cloud or not, or if it's a shadow or not. when shadow falls on water, or if it's moist vegetation or moist or soil, for example. Moist soil is also quite dark. Dark background, dark shadow, it's impossible to tell. So not as easy, basically. And what we did is basically we had a dense net, and we tried to fit the data inside. We had an accuracy of 99.4%, but we also know that there are still some overfitting here. Yeah. So actually, what we have to do is go back and get more training data. But what we figured out was that well, you never really know what the model looks at. So one solution is here that you create an occlusion. What does it mean? You have your model, and you create like a moving window where you have a black square, and you don't show certain areas of the image to the model, and then you see how good is the prediction of the model. And what we learned is that the model itself doesn't look at the shadow like we humans do, but the model looks directly at the turbine, at the engine, where the three wings are connected, because also there, when you close your eyes a little bit, there's also like a rainbow effect within this tiny 2, 3, 4 pixels, it's not more. And the model is just looking basically at this small area to detect if the whole thing is moving or not. But we humans, we don't see this. We need the long shadow, the bigger picture, to actually say yes, no, yes, no. Yeah, so we learned this, but yeah, this is an ongoing, let's say, investigation, so we need more data. Ideally, we would get logging data from the wind power providers or the owners. They are logging and they get data every, I don't know, 60 seconds. Is the windmill turning or not? And does it produce energy or not? So we would like to have this logging data, match it with the image recording dates or recording times. I mean, with Sentinel and the metadata, you know exactly at which second the satellite was overpassing. And then we could have beautiful training data sets to redo this analysis. And yeah, I think it's kind of useful to map the activity of windmills. I mean, this is not only limited to Germany. You could run this worldwide if you want to. Yeah, I think that's the last slide. Sorry for the technical problems in the beginning. Are there some questions?
Thank you very much. Are there any questions? We have maximum 2 questions. We can make 3.
Thank you for your presentation. On the first part, I was unclear whether did you use all your training data for training the model, or did you keep some for validation apart? And then, isn't there a bias if you reuse your results to actually retrain the model? Wouldn't it be better to correct your initial training data by looking where there are errors, and if the error is really due to a point that was misplaced, just replace it, rather than using your results from the first run to rerun a second run?
To answer your first question, I think in this data paper, there are 29,000 points, and we used around 8,000. And of course, we splitted them in training, test, validation. And we selected them randomly, and yeah, it's all valid. We were thinking about your second question as well. Can you use your result from the first model basically and retrain the model to improve it? I think there's a proper term for this. Is it trend? No, it's not. But I think it's a kind of common practice in the community to do this kind of approach. We were also skeptical in the beginning, but it's. I think when you read the papers, I think people do this.
I'm assuming aerial imagery is widely available in Germany. So why use planet-based maps and not aerial imagery? I bet you discussed this. I'm just curious.
That's a good question. I mean, so in Germany we have this top 20 data. It's meaning it's an aerial photo of 20 centimeter resolution, which sounds perfect for this case, but these kind of images are taken every 3 years. And 3 years, it's just too long. We have to wait too long for the next round of images. So what the people at the agency want is a monthly update. So we need a monthly product, and Planet is just providing it. Yeah.
Are you looking into detection of photovoltaics systems as well to correct the location and size?
Yes. So, so what in this AI lab, what we have is we have 6 months for certain use cases, and we finish this use case next week, and we start the week after to not only the detection of photovoltaic. We're not looking at the rooftops. We are looking at the photovoltaic in the countryside, the big ones. There are a lot of questions about the location and the model sizes, and is it fenced? Is it not fenced? Does it have any effect on the biodiversity and so on? Yes, we start a new use case, and maybe next year, next GeoPython conference, we can show some results of this exercise.
Okay, thank you very much again.